So good evening from Bangkok. Welcome to attend AIGS Free Gemology webinars to fight COVID-19 boredom. I am Michelle. This is our fourth webinar. Hope you enjoy it as usual. Before we start, I'd like to strengthen webinar issues again. We got some emails asking where to register the webinar. So as we mentioned, you could always find the registration links in AIGS website, Facebook, or WeChat. So today, by the end of the webinar, we will put our next webinar in the chat group. We will put our registration link there. So please pay attention to that. I'd like to remind everyone also, for each webinar, attend in 15 minutes before. So that means if you want to enter in earlier, you can't enter in, it doesn't work. So after the guest presentation, we will have a polling session also. So it's just a small game for interaction. So it's anonymous also, don't worry about that. Then after the polling will be the Q&A session. If you have any questions, please put in the question and the answer session. So after the presentation, we will try to select some questions to answer. And now, today I will send you after the webinar, tomorrow I send you the follow-up email. We will share some links of the social media contacts of our organizer and the guest speaker. So if you have more questions, you can contact us. So now I will give the stage to Mr. Kennedy Ho, AIGS chairman. So he will give a brief introduction to our guest speaker, Dr. Thomas Henchwa. So welcome, Mr. Kennedy Ho, chairman.
So I'm on?
Yeah, your turn now.
Okay. Sawadee. So, welcome back to AIGS Gen Tips. We are in Thailand. We are getting into our fourth week of our lockdown. And I'm sort of looking forward to getting back to work. So AIGS is going to reopen on the 5th of May. So about 10 more days. Today also we have a full house. All 500 seats are booked. And just a reminder, we received many emails that they tried to log in 2 days before. So maybe many of the attendees are not used to these webinars. You need to log in. Our webinar starts at 7 p.m. Bangkok time. That means the doors will open around 6:45 and everybody can start logging in around that time. We had a few emails like 3 hours ago. They said they cannot get in because you cannot get in because the seminar hasn't started yet. The doors are not open yet. So everybody maybe please 6:45, the doors open and everybody can start logging in. So for our next speaker, okay, from Liechtenstein. Okay? I don't know a lot about Liechtenstein, okay, but I know one thing. There's one very, very, very good gemologist there. His name is Dr. Thomas Hainschwang. I can vouch for him because he has written more than 150 articles regarding gemology, and he has presented more than 100 of those all over the world in different conferences. In 2015, he received the prestigious Antonio Bonanno Award for Excellence in Gemology. In 2017, he received the Gemological Excellence Award from the Swiss Gemological Society. You know, these awards are only given to people that have contributed significantly to the gemological world. I think Thomas is also one of the experts in the world regarding diamonds, especially for colored diamonds. So I think he's more than qualified to give his talk today on brown diamonds. So thank you, Thomas, for contributing for all the people that are very, very bored at home with this a COVID-19 mess. Okay, thank you again, Thomas. So I will give the floor to Thomas, and everybody stay home and stay safe at least another 10 days. Sawadee krap.
Okay, hi everybody. It's a pleasure to give this talk today. Big advantage of this webinar is if you're really bored, you could fall asleep without everybody seeing it. So I hope you won't. It will be quite a bit of spectroscopy as is brown diamond, but I think I can probably get some interesting insights into this topic. So again, good morning, good evening, wherever you are around this world. We're in the middle of the day. It's 2 o'clock in the afternoon. I'm actually sitting in the office. And I'm going to give a talk on our latest project. We've been working on fancy color diamonds for many, many, many years, and brown diamonds have been one of my topics that I was interested in since a long time. But I haven't really worked on them that much anymore since 2004. Obviously, always working on them, but not like as a new research challenge. So a few months ago, we started working on this topic again, and in order to create like a real in-depth look of the properties and the classification of brown diamonds. Now let's start with the simple definition of the color brown. Brown is not a spectral color. It's a color that's created by mixing spectral colors. A spectral color, just to define it, is one that you can represent by a single wavelength of the visible spectrum. Brown obviously is not part of the visible spectrum. Brown, in contrast, can be created by mixing spectral colors, actually complementary colors. So you can mix purple and yellow, blue and orange, red and green to create brown color. Or if you introduce black as a color, then mixing red with black or orange with black will result in brown color as well. So just a very dark and relatively low saturation orange and a very dark, relatively low saturation red will be perceived as brown. Brown as such, since it's not just a simple color, but it's a range of colors, can lean more towards various colors, including orange, red, green, and yellow. So you have greenish yellows, greenish browns, orangey brown, reddish browns, yellowish browns, etc. How does that look like on diamonds now? Here's a range of brown diamonds, a suit of differently colored brown diamonds, and you can see straight away that they're not all the same color. First of all, they occur in a very large range of shades, from very light to very dark. They have various saturations, from very low saturation to higher saturations, and with various modifying colors. And here on this image, you can see there is yellowish modifying colors, pinkish, orangey, reddish. So that's basically what you can see very commonly in brown diamonds. The color saturation is generally relatively low. The higher saturations are typically found in stones that have significant modifying color. So like orange brown diamonds tend to be much higher saturated than regular brown diamonds. Now let's give you some background information on brown diamonds. Brown diamonds have been studied in the past, particularly because of the HPHT treatment. Before, actually very little has been done on them. The most interest has been triggered in those diamonds to understand, and first of all, to understand the treatment, and second of all, to be able to identify the treatment. So during the various studies, it became clear that all brown diamonds that react well to an HPHT treatment owe their color to defects that are related to post-growth plastic deformation. Post-growth plastic deformations basically create slip along the octahedral crystal planes, and the slip planes created by such deformation are extremely rich in dislocations and vacancies. The color itself there were many, many theories out there that said, well, it's just deformation. You take a diamond, you plastic deformation. It's the plastic deformation. It's the slip itself which creates the brown color. All of those have been basically found to be not accurate, and it was found that brown color is actually caused by vacancy defects. It's not a simple vacancy. Vacancy, just to explain briefly, is if I talk of vacancy, I talk of the carbon vacancy. So it's vacancy not in its spot. So it's kicked out of the lattice, puts itself in an interstitial position, so in between the atoms. And the site of the carbon itself stays empty. This empty site is called a vacancy. Now the brown color is not caused by a simple vacancy, but by a very complex, large spherical aggregate of vacancies. They call it vacancy clusters. Now, these vacancy clusters are far more stable than a simple vacancy. Simple vacancies start to anneal out, diffuse and anneal out from about 500 degrees upwards, 600, 700, 800, 900 degrees. The simple vacancy disappears in a diamond. A vacancy cluster is very stable. And the only way to eliminate a vacancy cluster is by exposing a diamond to a temperature from about 1,900 degrees up. And this is done by HPHT treatment. Now, there are some brown diamonds that are colored by defects which are not related to plastic deformation. Such stones, in contrast to the stones that react to HPHT treatment, barely do anything with standard HPHT treatment unless you go to extremely high temperatures where you start modifying the nitrogen aggregation state. But since they don't have plastic deformation-related defects, they don't react to a treatment at about 2,000, 2,100 degrees. Why did I decide that we have to make this study? Actually, it's related to two things. First of all, we're getting more and more and more brown diamonds in the past years, mostly in small sizes, a lot of melee testing in brown diamonds. The first time I studied brown diamonds in detail was between 2003 and 2004 for my university diploma with Emanuel Fritsch, which I did on classification and color origin of brown diamonds. This study has been done with an equipment with a laboratory. Let's say it was not really comparable to what we have on hand now. It was much less equipment, much less material to test. So today, with a large quantity of stones we have, first of all, the large quantity we have in the collection, and all the equipment available, it gave us an opportunity to give an overview, a much more comprehensive overview of what has been done in 2003, 2004, and to review the brown diamond classification as proposed in that work. Now the sampling for this study, we selected 60 brown diamonds of all types and known classes, ranging from 3 points to all the way to 61.56 carats. Only stones with dominant brown color were tested, no olives. So all those mixtures of yellow, green, brown, and gray, I kept them out because they're somewhat different to actual browns, even though some of them really draw very much towards brown color. But I left them out on purpose because otherwise this paper, this work would be, instead of a 35-page paper, it would be 60 pages. So I had to keep it kind of down. So this is why we kept olive out. The samples are partially from my own collection. Samples were collected from the late 90s until just now. And the second part was filled in from a total of more than 30,000 melee-sized diamonds that we could screen and actually buy samples out of it for specific properties. So that's how we filled in everything that was missing in the collection so far, and to get a more varied overview of what's typical in brown diamonds. And then I added 1 or 2 individual exceptional stones that have been tested at the laboratory. What tests did we perform? Here's a list. It's basically everything you can pretty much do. Immersion microscopy with without polarizing filters, and then all types of spectroscopies from the UV via near infrared, infrared, PL with as many lasers as we can possibly use, fluorescence imaging with our fluorescence microscope, 7 different excitations between 220 and 405 nanometers. So we tested the diamonds in great details to properly characterize them. Let's go straight into it, and let's start out with brown diamonds with deformation-related colors. So I abbreviate those as DR, because otherwise you write out deformation-related all the time. Deformation-related diamonds are the ones that react properly to or positively to HPHT treatment. Here, the first slide shows you such diamonds in immersion on the left and in immersion with cross-polarizing filters in the exact same position on the right. Now these are like the two most typical ones. There's type 1A diamonds and there's the type 2A diamonds. Type 1A nitrogen-free or practically nitrogen-containing, and type 2A virtually nitrogen-free, at least via infrared spectroscopy. You can see that both of those stones have those lamellar color zones. These color zones are often called graining. They're like brown to pink graining. The top stone somewhat pinkish, the bottom stone somewhat yellowish. And this so-called color graining is parallel, first of all, it's parallel to the octahedral crystal planes. And second of all, as seen in immersion, you can see that in these lamellar planes, you have a distinct extinction, light extinction on the cross-polarizing filters. So this means that you locally interrupt the isotropic character of such diamonds, and they're actually anisotropic locally. This is why you have a black extinction along those colored lamellae. And that's one of the most characteristic things of such diamonds. Now, another very characteristic thing, now we're getting straight into spectroscopy, is that virtually all type 1, not type 2, DR brown diamonds exhibit strong absorption around 4,000 wave numbers. You can see here in the inset, you can see that recorded at room temperature. This defect is known as the amber center, obviously because it's present in brown diamonds mostly. And this diamond center, I worked on this diamond center in my work in 2003, and Dr. Laura Massi worked on this center in his PhD thesis, I think like a year later or 2 years later. And so it has been studied quite a bit. Here you can see a range of what you see in type 1B diamonds and in type 1A diamonds. There is basically 3 different zero phonon lines visible at room temperature, 4165, 4112, and 4065. 4230 wasn't sure if that was actually a zero phonon line or not. You'll see later why it's kept as a non-zero phonon line. This center is present in browns, and upon HPHT treatment, almost completely disappears. So it's clearly and directly linked to the vacancy clusters, but also to nitrogen, since we have it only in nitrogen-containing diamonds. Type 2 diamonds don't contain them. Now, without using our near-infrared spectrometer, we recorded all the amber center absorptions of those diamonds that you've seen just before at low temperature. And low temperature spectroscopy basically, first of all, proves that these are actually electronic transitions and not vibrational centers, as the many defects in the infrared are. They strengthen very strongly and sharpen very strongly. So you can see these are exactly the same stones in the near infrared, and you can see that the zero phonon lines multiply. So you have several of them afterwards. At low temperature, we can detect 5 different zero phonon lines, and you can see that the band at 4,230 did not increase. It stayed a broad band, hence it's not a zero phonoline, but just a vibronic side band of these complex defects. Here a close-up. So this is the samples, just the zero phonolines themselves, and you can see how they look like. So there is one that's absolutely characteristic for type 1B diamonds. That's the one at 4,111 wave numbers. The other ones can be present in type 1As or in type 1Bs. The 4111 zero phonoline I have not yet seen in a type 1A diamond. It always seems to need single hydrogen in order to produce this one. The other ones can be found in any type of diamond. 4136 I'm not quite sure about. So this is the low temperature work we've done on the Amber Center. You can see here on the left in the trace A, there is H1B zero phonoline. That might be surprising for many, that you find H1B in just a brown diamond. I assure you the diamond has not been treated. H1B is a very, very common defect in brown diamonds, particularly the ones that have the 4063 zero phonon of the Amber Center. So we found H1B and also H1C in such stones. Here an overview of the UV visible spectra of brown diamonds. You can see that the brown color originates from a relatively shallow and flat continuum absorption that starts in the near infrared and extends all the way to the UV. The steeper this continuum, the more saturated the color. The more overlaying features you have, the more modifying colors you're gonna observe. So here, for example, in trace C, you see a band at 560 nanometers. That's why the stone is somewhat pinkish, as you can see in the image. And then there is others that barely show anything, like trace F is basically just a continuum with very minor features. And you can see that depending on what type the stone is, the UV visible spectrum varies somewhat, but they all coincide in the fact that they're mostly just a continuum, a flat continuum, which is the result of brown coloration. Type 2A diamonds, you basically see the same thing, just that the overlaying bands are even much less frequent. So for type 2A diamonds and type 2B, also there's type 2B diamonds here as well, you see just a couple of broad bands that overlay this continuum. The pinkish one, sample D, is kind of exceptional because that's a stone that shows photoluminescence that has been assigned to oxygen. They have created that by oxygen implantation in natural diamond, and this is what we found in natural untreated diamonds. So these are the relatively unspectacular low temperature spectra of type 2 diamonds. Going to photoluminescence from here. Here you see the fluorescence image of this diamond, this pinkish brown diamond. You can see it's mostly pink with some green and some blue in some corners, and the correlating photoluminescence spectra. Now, these PL spectra have been recorded in a range of lasers, 402, 473, 532, 635. And the most interesting ones are the ones in the lower wavelengths, because you have the most information in them. You can see that this strong pink fluorescence is caused by a very broad band centered at about, it's around 750 nanometers. This broad band has actually been found to be present in absolutely every single brown diamond that's type 1A. A type 1A brown diamond without this band is either extremely low in nitrogen, then the band might be undetectable, but all diamonds that have, let's say, more than 50 ppm of nitrogen, aggregated nitrogen, we have found this band, particularly strong in type 1AB samples, much less strong in type 1AA samples. This broad band is very likely the vibronic structure of either 617.6 or 626.30 phonon lines. These always occur together and correlate in intensity. It's quite likely that one or both of them are 0 phonon lines of this structure. So whenever you see funny pink fluorescence in a brown diamond, that's what causes it. Now, the intensity of this band obviously determines whether the final fluorescence that you see is pink or green, because as you can see, you have also, or blue or green, you have N3 centers, which cause blue fluorescence, and you have H3 centers, which cause green fluorescence. Now here, the very dominant defect under this excitation is the 715, hence you have this pink fluorescence. Here the PL of a type 2 diamond. Now I show this is actually a type 2B, hence a boron containing brown diamond under different laser excitations. You see the spectrum is quite different, but this is not something that's highly characteristic. Now this is a highly characteristic spectrum for a type 2B stone. Type 1A stones may be very similar to this, but type 1A stones may be also very similar to what you see in other type 1, low nitrogen type 1 diamonds. You see many defects, a big overlap of the defects in type 2 and type 1 diamonds, except this broad band at 710 that I have not personally seen ever in a type 2A diamond. The reason for that is type 2A is not always type 2A. Type 2A contains some nitrogen, some more aggregated than others, so it can be very variable. It's basically a continuum from type 1 towards type 2, and since we can only determine the nitrogen content with infrared spectroscopy, it's kind of a limited sensitivity. So this is an example. GR1, irradiation peak, very typical, stronger in type 2 diamonds than in type 1 diamonds. Yeah, this is much about type 2 diamonds. Let's have a look at the fluorescence of DR brown diamonds, deformation-related brown diamonds. These are type 1 AAB stones, 2 samples. You can see they're very different here. If you look at the PL spectra of these stones, they're actually quite similar, except that the ratio between the different photoluminescence peaks are very different. In the top stone, N3 and H3 plus probably 490 nanometer band is probably very dominant, while down here we have seen the 715 nanometer band is very dominant. You can see the deformation-related graining here. So these bands that you see here on the top spectrum go straight along the slip planes. They contain usually at least H3 centers. So you have H3 and H4 centers in these stones that cause predominant green fluorescence that's very commonly seen in brown diamonds. More or less intense. You can have brown diamonds that have such strong green fluorescence that they basically have the same effects like a green emitter, but just with a brown body color. Sorry, that was one too much. There we go. And now here we have PL imaging of type 1B top and type 2 bottom diamonds. Now these are just, the bottom one is just a spectacular example because very often type 2 brown diamonds don't have a very, not a very characteristic kind of fluorescence image. They actually are very similar to type 1 stones, except that the fluorescence is often much weaker. This stone has very strong H3 centers, even though it classifies as type 2A under infrared spectroscopy. So it has a relatively high concentration of H3 centers. And you can see the dislocations of the diamond in the image at 220 nanometers. The 1B diamond, those stones are highly unusual actually. Type 1B, really just brown diamond, plain brown diamonds are very unusual, and they always fluoresce strongly orange-red from the ND center itself that dominates in these kind of stones. Now let's have a look at brown diamonds with non-deformation related color. I abbreviate that with NDR. So there is quite a big range of stones that show brown color, but no deformation whatsoever, or almost no deformation whatsoever. Let's talk about a class of diamonds. We worked, actually it was Frank Notary and myself who was involved, Emmanuel Fritsch was involved. We worked on these diamonds quite intensively in the early 2000s, 2003, 2004, 5, 6, but relatively little was published in the end about them. There are so-called CO2 diamonds, and the class that actually I defined in 2003 as Pseudo CO2. The reason why Pseudo CO2, they have exactly the same properties as CO2 diamonds, but don't show CO2. Now I'll show you where this CO2 can be seen in those diamonds. Let's look at the immersion first of all, so you see what's the difference between these and deformed brown diamonds. The most typical CO2 diamond shows the color distribution as you see on top. It's typically a color patch that's somewhat inhomogeneous, non-homogeneous in distribution. If you put it in the cross polarizers, you can see that the extinction, there shows up some extinction that's very likely inclusion related in these stones. You can see there's colorless areas and there's brown areas. The brown areas are the ones that are rich in CO2. The colorless areas are actually CO2 free. Then on the bottom you see what we call pseudo CO2 diamonds. These diamonds often, instead of a color patch, have colors, some sort of color zoning. They're parallel. Do not relate to extinction patterns from deformation, but they show a couple of bands that actually show strong extinction. You can see on the left side in that diamond in the middle, there is one plane that's kind of olive gray in color. That olive gray plane is the one that extinguishes completely, gets dark. And upon rotation, every 45 degrees, it will go light, dark, light, dark. So these are the only bands that do this in these diamonds. Very unusual diamonds. And now I'll show you why these are called CO2 diamonds. The top three traces, A, B, and C, are all CO2 diamonds. In all those diamonds, you can see absorptions related to CO2. Now the CO2, it has been speculated, is present as inclusions. It has been speculated, on the other hand, that it might be not inclusions, but actually structurally bound CO2, or even both of them. It's still not quite clear what it is. I explained some of the reasoning behind this. What we call pseudo CO2, the last trace. From the trace itself, you can't really relate why they would be, identical or very similar. If you take a pseudo CO2 diamond and you subject it to HPHT treatment, that's one paper that we have published, the stone will develop CO2 absorption. So there you go. And also, all the properties of the stones are virtually identical, as you will see in some of the following slides, especially the luminescence and absorption spectroscopy of those stones. Here is the absorption spectroscopy of them. We have 3 pseudo CO2 diamonds and 2 CO2 diamonds. And you can see that the spectra are very, very similar. They all contain a weak 480 nanometer band, a band that has been assigned to oxygen defects in the past. They all have a 427 nanometer band, something we also see correlated to 480 nanometer band, to the 480 nanometer band. So this is the typical kind of spectrum of a CO2 and pseudo CO2 diamond. The diamonds can be relatively variable in color, simply because of the shape of the slope. They can range from just about anything to anything. We have seen pinkish, we have seen reddish, we have seen brownish, yellow. From time to time, they go out of the brown range, but generally such stones are brown. Here the fluorescence of such stone. So this is the PL spectroscopy. The PL spectroscopy, the most interesting band in here is that wiggly band centered at about 690 nanometers. This band is known from many oxygen-containing diamonds, from those typical orange, yellow, so-called 480 nanometer diamonds. They contain this band. There's lots of nickel-related features in these spectra. The yellow fluorescence itself that you see visually comes very likely from the S1 and S2 center absorption, which you can see in trace A on the left side. So that's what the yellow fluorescence originates from. Here you see a pseudo CO2 diamond as comparison. The two are virtually identical. I mean, there is obviously differences since those spectra are highly complex, but overall, they're pretty much identical. You can see in trace C at 473 nanometers, we have exactly the same 680 nanometer band as we have seen in the CO2 diamond. And note also the intense nickel band at 884 nanometers, something very common in brown diamonds, not only in synthetic diamonds. PL imaging, here we have two samples, a CO2 diamond on top and the stone that's actually limit between CO2, pseudo CO2. They have sometimes rather dramatic luminescence images, as the bottom stone shows. At 220 nanometers, I mean, it's like a piece of art, this kind of fluorescence image. Okay. Now let's have a look at hydrogen-rich diamonds. Hydrogen-rich diamonds are another class of diamonds that can be brown. Hydrogen is very common in diamonds. It has been brought into in correlation with many different colors. We have yellow stones, we have violet stones, we have brown stones, we have olive green stones that are hydrogen-rich stones. Chameleon diamonds are hydrogen-rich very often. So there is a range of diamonds that are rich in hydrogen. Let's have a look at those stones. Now, here we are, as I showed two classes of hydrogen-rich diamonds. One of them on top. The bottom stone is from Zimbabwe. It's one of those mixed cuboid octahedral stones, so-called asteroidal diamond. And the bottom one, the top one is just hydrogen-rich. So the top one on the cross polar in immersion shows barely any color zoning. So the color is relatively homogeneous in these stones. And on the cross polarizing filters, you don't see any anomalous double refraction in such stones. So there is no strain. There is nothing. These stones don't lighten up. They don't get dark. They just stay dark like an isotropic stone is supposed to do. So that's the first type of hydrogen-rich diamonds. And the second type is the cuboid octahedral stone, where you can see all these strain patterns between the actual arms, if you want to call them arms. This is likely caused by the strain induced by the different growth sectors, just like you can find it in certain cubo-octahedral synthetic diamonds. Interesting, very interesting is the infrared spectroscopy. Now in the infrared spectroscopy, we have always seen, okay, they're rich in hydrogen. So we have those peaks, those sharp peaks at 3107, 1405, all the overtones and combinations that you can find. And always there was a broad band at around 7,500 wave numbers. There was some funny broad band in certain hydrogen-rich stones. Now, with our new capacities to go low temperature in this range, we recorded here infrared spectrum that ranges all the way to 900 nanometers. And the entire range from 4,000 wave numbers to 11,000 wave numbers is low temperature spectroscopy. So this band at 7,500 nanometers actually is split at low temperature, splits into a doublet at 7,514, 7,457 nanometers, and a very strong vibronic component that ranges probably to about 1,000 nanometers. not sure if this center is the actual cause of everything that happens afterwards in the visible, because it's actually, when you look at the whole spectrum, which we've also done, we've normalized the entire spectrum all the way to the visible. The 7,000, the band here in the near infrared is by far the strongest feature of the entire absorption spectrum from the near infrared all the way to the UV. So this is a very significant peak that has, to my knowledge, I have not seen a low temperature spectrum of it yet. So this is a very, very interesting spectrum, and it actually defines this type for us. We call it the 1330.8, 1340 nanometer type. Compared to this, the other H-rich diamond, which we call the 3310 centimeter minus 1 type, because that's what distinguishes them. The normal H-rich stone we've seen before has a relatively simple hydrogen spectrum with mostly 3107 plus 3238 and all combinations and overtones. This stone in the brown sectors shows a much more complex spectrum that's actually related straight to cuboid growth. So in cuboid growth, you find these type of hydrogen infrared absorptions. And just to show that this is actually factual, I took spectra of the colorless sectors and spectra of the brown sectors. The spectrum of the colorless sector can be seen as spectrum B, and the brown sector is spectrum A. Spectrum B barely contains any hydrogen compared to spectrum A. It's still hydrogen rich, but compared to spectrum A, very little. And all the cuboid growth related peaks are actually absent. You can see this is a plate, a very thin plate, and that's why we were able to resolve the entire nitrogen absorption with a humongous absorption coefficient of about 170 centimeter minus 1. And then here, this is a rather exotic one, but if you have to deal with specific client demands, and we know that certain of our clients have to deal with such client demands, when, for example, you have a client that wants to have a dark orangey brown diamond, I wish you good luck finding those in quantity, because those are the only ones that will satisfy this kind of color. So you have dark or deep orange brown color. These are rather rare type 1B XY, we call them, because their one phonon absorption is not a typical 1B spectrum, but it's much more X center plus Y center. I explain in a second. They are hydrogen rich, as rich as type 1 stones ever get. The hydrogen relates not at all to the single nitrogen, but it relates straight away to X center and Y center. The X center is nothing else but positively charged single nitrogen. The Y center is a defect of unknown nature. Now here we can see at 1142 wave numbers. If this was a C center is found at 1130, precisely 1130. In nearly all natural type 1B diamonds, the C center absorption is found somewhere between 1132 and 1145. If it's 1145, then you're actually sitting straight on the Y center. And if it's somewhere in between, then you have a mix between Y center plus C center. In all cases so far that I've seen, you always see a little bit of C center. And you can see the C center in this spectrum with the peak at 1344 wave numbers, and in front here in the near infrared at 2688 wave numbers. If you calculate the nitrogen content, you will find out that the absorption, the one phonon absorption, is way too strong for a quantity of nitrogen. And you decompose it and you'll find this famous Y center. Now these stones are the ones that we classify them still as brown, and the only ones that we would call H-rich type 1B diamonds. Okay, let's have a look at the UV visors. Now this is a really famous stone that shows probably the most beautiful of those UV vis spectra. That's a hydrogen-rich diamond of that 1330.8 1340 nanometer type. So the one with the near infrared absorption resolved before. And you can see the 900 nanometer peaks that we have seen in the other spectrum and how this spectrum continues. It's a very complex spectrum. It also causes a continuum. This is the tiger's eye diamond. It weighs 61.56 carats. Probably it's for sure the biggest gem quality, high quality, gem quality, hydrogen-rich diamond in existence. It's not strictly speaking brown. It's really a mixture between yellow and brown, like many of them are. Many of them are a mixture between, you know, like olive, yellow, brown. And this one is a mixture between yellow and brown. Beautiful stone. So this is that kind of spectrum. So all these diamonds have this complex, wiggly spectrum. In comparison to this, the cuboid octahedral stone, the astriated diamond, here spectrum A is of the brown sectors, spectrum B is of the colorless sector. Colorless sector, you can see there is just nothing. It's just no absorption whatsoever. And then at 330, you get up to the cutoff at about 310 nanometers. The brown spectrum is a very shallow continuum with a flat band at 435 nanometers, virtually no M3 centers present at all. A couple of weak peaks overlaying the spectrum, most likely, most certainly, I would say, related to nickel. These stones, you put them in an EDXRF and you actually can measure the nickel in them. So they are relatively nickel rich. The color itself, I really don't know what it originates from, if it is possibly nano inclusions related. I'm not quite sure about that, but it's very, very, very different to what we know from other hydrogen-rich diamonds. Let's look at the PL of such stones. The PL color can be somewhat variable from stone to stone. Here we see like a greenish yellow PL from this broad band back here with the different features at 522, 527, and all that. And the strongest features of these stones are the 700.6 nanometer zero phonon line and its vibronic, and 787 and 793. A lot of what we see here is, like with the other sample, nickel related. So nickel is a very common thing in hydrogen-rich diamonds. It's quite speculative, but it seems very likely that absorption spectra of this type hydrogen-rich diamond is related to a nickel defect. Often you hear hydrogen-related color, but I highly doubt that hydrogen causes UV visible absorption in this range. It might be a defect that involves all of the above, nitrogen, nickel, and hydrogen, but certainly not hydrogen alone. Here, the same thing of the cuboid octahedral stone. The green fluorescence that's so spectacular in these stones and always is confined to the brown sectors or to the arms themselves. This green fluorescence originates from the S3 center. You can see it in trace A. This broad band centered at about 540 nanometer translates directly into green fluorescence. The S3 center is nickel related. So again, you can see nickel is quite important in brown diamonds that are hydrogen rich. Here are the two PL imaging images for those two samples. You can see the cuboid sectors fluorescing green of this type, and here we can see this irregular type of yellowish green fluorescence in the other type. Okay, now let's get to our classification of brown diamonds. This is the revised classification of the original classification done in 2003. Here we go with the list. So it's basically is what you could have seen in my presentation so far. We got the two broad groups: deformation-related brown diamonds and non-deformation-related brown diamonds. And these ones can both be subdivided into 5 types each. So you have type 1A, type 1 and type 2 for deformation-related diamonds. And there we have the subdivisions depending on what type of amber center is present. So here we have just a simple amber center. Here we have a double amber center. Type 1B is characterized by this 41112 amber center. Type 2, none. Well, I'm not going to go into all details of this table. Most important is the different class names. So we subdivided them into single amber center, double amber center, single amber center 1B, then type 2A diamonds, type 2B diamonds. The non-deformation related diamonds are classified by type 1 and or undefined type, because in CO2/pseudo CO2 diamonds, sometimes you have cases where there is no nitrogen related absorption distinguishable. So you cannot actually define what type they are. And then in the other types are the hydrogen rich stones that are type 1AB, which are subdivided in the cuboid octahedral and in the standard ones with the 1330.8, 1341 nanometer bands, and the cuboid octahedral ones, and the hydrogen-rich type 1B diamonds. So this gives a total of 10 different classes of diamonds, and you can fit pretty much any diamond that you're looking at. If you're looking any brown diamond out there you're looking at, you can fit it in this scheme without any problem. The only ones that might be kind of limit sometimes is if you have an orange-brown stone with a strong green fluorescence. You might, in certain cases, not find an amber center in them, but that's like really the only exception to the rule. The rest will certainly fit in every single one of these proposed classes. Okay, let's go out of the direct study and let's go back into it first, and let's look at how can you have a brown diamond that's treated. I've been asked this question many times. It's kind of unusual, but it actually exists. So this is not how do you change the color of a diamond by treatment, but it's actually how do you get a diamond brown by treatment. I'm just going to show the spectrum and I'm going to talk about it. Okay, these are 3 stones that are all brown and treated. A is like an orange brown, B is a yellowish brown, and C is an orangey brown stone. They've all been produced by treatment. A has been produced by neutron irradiation. That stone was perfectly colorless before treatment. We treated by neutron and made it black, opaque black, I mean, really black. And then we annealed it to 1100 degrees. At about 800 or 900 degrees, it got this beautiful orange-brown color and this very complex spectrum seen in trace A. So this is one way. Basically what happens, you see those many peaks in this spectrum. These many peaks have actually relatively little influence on the actual color that you can see. The main color comes from the continuum. Continuum is relatively steep, hence the stone is very orangey and not just brown. This continuum comes from the high density of vacancies that's being accumulated by heavy neutron irradiation. That's actually something that happens by any type of heavy irradiation. So you can see that also in green diamonds. But if you irradiate the stone heavily, you will always keep a continuum. And this continuum is from some sort of it's a defect that must be very similar to a vacancy cluster. It's an accumulation of many vacancies that's relatively high, relatively stable to high temperature treatment. And this continuum will only anneal out at about 1750 degrees. So it stays, the stone stays basically the same color until you go above 1500 at least. And then you start seeing the continuum disappear. So it's a highly stable vacancy related defect as well. The other 2 samples are to show you what happens if you treat a stone that has been brown at the beginning. That's stone number B. Stone number B was brown before treatment. Probably the dose of irradiation was not high enough in this case. It's a stone that we have treated. I think it was just 2 MeV irradiation and not long enough. And the stone was somewhat dark before treatment. So if you treat your stone, a brown diamond, by irradiation, and then you start annealing it, this one has been annealed only to, I think, like 800 degrees, if I'm not wrong. Then the defects you need in order to create a more attractive, or let's say a different color than brown, will not be formed. So in this case, we have created barely anything that will change the color from the continuum. If you want to change the color of a brown diamond, you need to create other defects strong enough on top of the continuum that the color will change. And this didn't happen here. That's why the stone stayed just basically brown. And then number C, that's one of those famous CO2 diamonds. Now this is a pseudo CO2 diamond. We have treated a range of those, and they actually never change. They don't change by HPHD treatment. They don't change by irradiation. You can induce some GR1 bands in it, but then you anneal it and nothing happens. These stones sometimes, or quite frequently, don't contain any significant quantities of nitrogen defects. The defects we see are not nitrogen related. So if you irradiate and anneal, you don't create the well-known nitrogen-related nitrogen vacancy defect and all these things that change the color in a diamond by treatment. Hence, a CO2 diamond very frequently just doesn't change. It stays the way it looked before. You can get brown diamonds by HPHD treatment. What we have done here we have taken Cape diamonds. Some of them were perfectly colorless, and some of them were yellowish Cape diamonds with very high nitrogen content, typical Cape diamonds, and we have submitted them to HPHD treatment at about 2,500 degrees, so very, very high temperature. And actually the colorless stones, that, as you can see in the spectrum down here, the colorless stones have AB, they have no N2, no N3 center absorption because they were actually DOE color. Post irradiation, post HPHD treatment, you only have a continuum absorption. In consequence, A star and B star correlates to perfectly yellow diamonds. So these ones were transformed by HPHD treatment from perfectly colorless into canary yellow. So they were as yellow as a canary yellow diamond. In contrast to this, the stones very rich in N2 and N3 center, N2 being part of the N3 center, obviously, were transformed into brown. And they were actually just slightly orangey brown was the final color of them. They were dark orangey brown after the HPHD treatment. And you can see what happened to the spectrum. The spectrum went from the N2 and N3 center spectrum into a continuum. But compared to what you see in trace A and trace B, the low N3 center samples, the high N3 center samples, you added a continuum on top of the regular C center continuum down here. Starts about 700 nanometers and goes all the way to the visible. And this added continuum is responsible for the brown color in these stones. Now the question is, where does this continuum come from? The lower N3 center samples after HPHD treatment actually had more C center content than the N3 center samples. So they shouldn't be, it's certainly not C center related. And then if you look at the spectrum, there's something significant to notice. The N3 center and the N2 center are absolutely absent from my UV visible spectrum. So I heard somebody saying, yeah, well, it's just a continuum overlaying the N2 and N3 center, which is absolute nonsense. The N2 center would be clearly visible if this was just a regular, you know, like if you have some C centers in an N3 center diamond, you will still see the N2 and N3 center after such treatment. The logical consequence is At such high temperatures, the N3 center is actually destroyed. And the added continuum, from a logical perspective, because otherwise those stones are virtually identical in defect, the added continuum must relate to whatever defect is created by the destruction of the N3 centers. Pity that the stones images are not here, but whatever. Okay, let's have a short talk about synthetic brown diamonds before I go a little bit into the enhancement of brown diamonds. In this study, we just added 2 synthetic diamonds just to add the stones as examples. Actually, untreated brown diamonds, really brown diamonds, exist only in CVD. There is no such thing in synthetic HPHD diamond that's actually brown. It's always a dark, dark yellow, or it's never going to be an actual real brown. Dull, light brown stones are very, very common in CVD synthetics. These are type 2A diamonds. Here you see it in the image D and trace D. This is the absorption spectrum of it. It's a very shallow continuum. This is a stone that's lighter than fancy light, so it's a relatively light color. Such stones are very, very, very common in parcels of melee diamonds today. So particularly the lighter range colors. The darker browns are basically unaffected, but the light ones is very common. This is the kind of color you grow, many CVDs grow, you know, the growers, they produce them in this color, and then they HPHT treat them to make them colorless. Now, melee sizes, I don't know how far it's worthwhile HPHTing them. That's why they basically throw them in parcels of natural diamonds, and that's how we get them here at the laboratory in the end. In HPHT synthetics, brown color can be induced by radiation. Here you see a sample. You take the best samples to start with is when you have an overly dark, relatively high nitrogen, and if possible high nickel containing synthetic diamonds. You irradiate a stone like that, it'll basically turn brown. It'll turn somewhat greenish brown. It's like an olivish brown color, pretty dark in this case. You can see what happens. Prior to irradiation, you have trace A. These are all nickel-related defects that you see here. The nickel-related defects are in part responsible for this overly dark yellow, brownish yellow appearing color. After irradiation, you simply overlay a GR1 band on top of the absorption, and in consequence, you have dark yellow plus green. Well, you know, that gives basically some sort of a brown. Now, just for the fun of it, we heat treated the stone afterwards at 800 degrees. And at 800 degrees, GR1 disappears, and you're creating strong NV centers at 637 nanometers. And the broad band that results from this is the reason why your stone after treatment appears brown red instead of olive brown. So these are the samples that you can get in synthetics. HPHT, you're never going to find one in a parcel ever. Probably never going to find one in the market. The CVDs are very common, and they will be even more common in the future to come. Okay, now, last but not least, I'll talk, give just a quick overview, because this is a subject I could talk another hour about, which I'm not going to do, I promise. Treatments to change the color of brown diamonds. Now, this is not what this study was about, but you know, we've been working a lot on treatment of diamonds, and part of them were obviously also brown. So I just wanted to include this. Treatment methods, what do we do to change the color of a brown diamond? We can irradiate them, we can HPHT treat them, and we can anneal them. Irradiation method most commonly used today is electron irradiation, because you basically put your samples in, turn the beam on, turn the beam off, go in, look at the samples. If they have the color you desire, okay, you can take them out. If not, you go out, turn the beam on. Don't ever forget to go out before you turn the beam on. And so, you know, it's relatively easy. It's much easier than neutron facility. In neutron facility, you can't put a diamond in. go in and check. You just can't. It doesn't work like that. And then neutrons, there's also always the risk. It could be radioactive afterwards. You have to store them for a while, etc. Electrons never render your samples radioactive, so that's actually easy treatment. Then heat treatment is just, you know, to consequently to electron radiation change the color further. We do this here at the laboratory directly. And then HPHT treatment, you use this kind of presses like here shown in the middle. It's a cubic HPHT press. Yeah, same thing that you use for synthetic diamond growth, HPHT synthetic growth. Let's have a look what happens when you irradiate a brown diamond. Many brown diamonds, there's a lot of them out there, and the market was not always very favorable to them, which seem really to change in current years. But quite a few of the lighter brown colors, when the color is not distinct, were used to irradiate. So you can create what's shown in this slide. You can take a light brown diamond, you irradiate it, it turns greenish blue. Depending on the radiation dose / energy, you create either a more blue or a more green color. And then you can heat treat them. And depending on what your stone originally looked like and how your irradiation was, you might induce a pretty yellow hue into your sample. Now that's one way of doing it. HPHT treatment, you take a brown diamond to start with. You heat treat it for a couple of minutes at 2,100 degrees, deformation-related brown diamond. It'll turn greenish yellow. Greenish yellow with strong green fluorescence. So, you know, like what we all know as a green emitter diamond. If you take the same diamond and you treat it instead of 2,100 degrees, you treat it at 2,400 degrees for a couple of minutes, the stone will turn orange or vivid yellow without any fluorescence, or basically no fluorescence. So what are you doing? At the lower temperature, you're destroying the vacancy clusters, and you're creating strong H3 center absorption and luminescence. The H3 center absorption and luminescence is responsible for the green fluorescence. If you go to higher temperature, you also destroy the vacancy clusters, hence the brown color. But at the same time, you're destroying any type of H3 or H4 center that might be created by a lower temperature HPHT treatment. And instead, you're manipulating the nitrogen aggregation state, and you're creating C centers. And the C center, hence the single nitrogen, induces this intense yellow color that you can create at higher temperature. So this is type 1 diamonds. So, if you take other HPHT treatment results, if you take a type 1B brown diamond and you HPHT it, it will turn yellow. If you take a type 1B olive diamond, you HPHT treat it, it will turn yellow as well. So these stones, same thing, their color, and even the orangey ones, you HPHT them, they turn yellow. All those color modifications in type 1B diamonds are all related to vacancy clusters, and all are annealed out by HPHT treatment. Most famous in the market, type 2 diamonds. Type 2 diamonds, they require a somewhat higher annealing temperature. So usually you go probably somewhere between 2,300 and 2,500 degrees Celsius, just a short time. Any type 2 diamond will turn into its color without the brown. So if you have a type 2A diamond that was light brown, it'll turn colorless. If you have a type 2B diamond that contains some boron at least, it'll turn anywhere between gray and blue. If you have a pinkish brown type 2A diamond, it might turn pink first. And if you treat it again, it will go colorless. So this happens with type 2 diamonds. If you take brown diamond, same thing, deformation-related brown diamond, and you HPHT it at high temperature, so you manipulate the type. You're creating a type 1A diamond with some single nitrogen. it's going to be yellow-orange in color, or somewhere in between yellow and orange. So you're creating from a regular 1A brown, you're creating a 1A diamond with some C centers. These C centers are needed to create purple color. And this purple color or red color is induced by irradiation plus annealing. Irradiation plus annealing of a single containing diamond. A single nitrogen containing diamond will always produce the NV centers, and the NV centers induce that pink to purple to red color. So this is a multi-step treatment that's being used since about, I think, like 2008 or 2009 to create pink to red diamonds out of a regular type 1A brown diamonds. Okay, I'm at the end of my talk. Let me give you a short summary and conclusions. As you have seen, brown diamonds include a very vast variety of diamonds of all types and classes. Brown diamonds contain a very wide range of defects, some of which are actually unique to brown diamonds. Based on all the data obtained, they show distinct color origins being either related to post-growth plastic deformation or not. The reviewed classification presented here shows that brown diamonds can be split into 10 different classes, 5 being deformation related and 5 being non-deformation related. There are some brown diamonds out there that are the result of treatments. Those are mostly orange-brown in color, although some of them are simply mishappen diamonds. So somebody treated something and it didn't work out the way they wanted it to work out. Synthetic diamonds, today, CVD synthetic brown diamonds are really widespread in parcels of brown melee diamonds, particularly in those parcels that are lighter than fancy light brown. On the color modification of brown diamonds by treatment, the most common thing you see in the market is melee, particularly melee in the blue to green range, where they use as a starting material, rarely they use colorless material, but usually we use brownish or yellowish stones. So brownish are cheaper, so why not using brownish? So that's just simply radiation. And in the case of type 2 diamonds, the D to F color range is the most common one where we observe stones that have been treated. In a laboratory, all those can be identified. In the very rare cases, type 2 diamonds cannot be properly identified as being treated or not, but most commonly we can solve all those problems in a lab. And I think with this, I finish my presentation.
I think this is a very academic talk in brown diamonds. It will be very helpful for those who are doing the research in the diamonds. Thank you so much, Dr. Thomas, again, for your great presentation.
All right, thank you. Thank you, everybody.
Yeah, thank you,
everybody. Hope it was not too long.
Yeah, it's okay, yeah. Thank you so much.
Okay.
Thank you for attending. Bye-bye.
Bye.